All right, if you're gearing up for JEE or NEET, you know some chapters just carry more weight. And let me tell you, work, power, and energy is one of those chapters you absolutely positively have to nail. So in this session, we're going to tear it down, tackle some really tricky exam problems, and basically give you everything you need to crush this section. Let's jump right in.
So think about this for a second. What on earth connects a car flying down the highway, an apple falling from a tree, and a spring that's been stretched out? It seems random, right? Well, they all have one thing in common: energy. You can think of energy as the universal currency of physics. It gets stored, it gets transferred, it changes form, but it's always there. Today, we're going to learn how to follow the money.
So here's our game plan. We're going to start with the absolute must-know core concepts. Then we'll get into the different types of forces. After that, we'll unlock the master key to this whole chapter, the Work-Energy Theorem, and immediately use it on real exam-level problems. We'll finish up with a super fast revision round, and then I'll show you how this all connects to what's coming up next. Okay, first up, the fundamentals. Seriously, think of work, power, and energy as your essential toolkit. You literally can't solve a single problem in this chapter without a rock-solid grip on these three ideas. Let's start with work. Now, in day-to-day life, work is, effort. But in physics, it's super specific. Work is only done when a force actually causes something to move. But here's the catch. It's only the part of the force that's in the same direction as the movement that counts. That's what that cos theta is all about. And remember this. Force and displacement are vectors. They have direction. But work? Nope. It's a scalar. Just a number. So that angle theta, it's a huge deal. It decides if the work is positive, negative, or even zero. Look, if the force is helping the motion, like gravity pulling an apple down, the work is positive. If the force is perpendicular to the motion, think about the string on a pendulum, it's doing zero work. And if the force fights the motion, like friction, the work is negative. This is such a basic concept, but they love to build tricky multiple-choice questions around it. Next up, kinetic energy, the energy of motion. We all know the formula, half mv squared, right? But listen, here's a pro tip, a real time saver for your exams. You have to know the relationship between kinetic energy and momentum. This little formula, k equals p squared over 2m, is an absolute lifesaver for questions that mix both topics. Burn this one into your brain. And last in our big three is power. Simply put, power is how fast you do work. Average power? That's just the total work you did divided by how long it took. But for instantaneous power, what's happening at one specific moment, we use the dot product of force and velocity. And remember, that dot product just means F times V times the cosine of the angle between them. All right, let's talk about the forces that are actually doing all this work. They basically come in two flavors, and knowing the difference between them is, well, it's everything. The big question you have to ask is, does the path I take matter? This table lays it all out. For conservative forces like gravity, the path doesn't matter at all. It just cares about where you start and where you end. But for non-conservative forces, like good old friction, the path is everything. The longer you drag something, the more work friction does. And this is the key. Mechanical energy is only conserved when you're dealing with only conservative forces. And now for the main event. If you want one single tool, one master key that can unlock even the most confusing mechanics problems, this is it, the Work-Energy Theorem. It's not just another formula, it's a whole new way to look at problems. And here it is. The net work done on an object equals its change in kinetic energy. And when I say net work, I mean the work done by every single force. Conservative, non-conservative, external forces, all of them. You add up all the work, and that tells you exactly how much the object's kinetic energy changed. It is that simple and that incredibly powerful. Okay, enough theory. Let's get our hands dirty and see how all this stuff actually plays out in the real world, or at least in the world of JEE and NEET exams. We're going to tackle a couple of problems that are exactly the kind of thing you'll see. Here's a total classic. You've got a force that's changing as the block moves. It's not a constant force, so you can't just multiply force times distance. So what's the plan? How do we solve this? So here's the topper's trick, the secret sauce. You don't need to do any complicated integration. Just remember, work done is the area under the force displacement graph. That's it. Just break the graph up into simple shapes you know, rectangles, triangles, calculate their areas and add them up. And don't forget, any area that dips below the x-axis, that's negative work. Okay, get ready for this one. This is a classic trap question. I've seen so many smart students fall for this. We've got a mass hanging from a spring, and you just let it go. The question is, how far down does it go? It sounds simple, but there is a huge pitfall. Let's break it down. So the trap is on the left. You assume the block stops where the forces balance out, where the spring force up equals gravity down. That gives you an answer of mg over k. And I guarantee you that will be one of the multiple choice options. But it's wrong. Why? Because when it reaches that point, it's still moving. It has kinetic energy, so it's going to overshoot. The correct way is to use energy conservation. The potential energy the block loses from gravity turns into the potential energy stored in the spring. You solve that and you get 2 mg over k. Exactly double the trap answer. All right, deep breath. Let's shift gears and do a quick rapid-fire revision. We're going to make sure all these key ideas are stuck in your head for good. Here they are, the essential formulas from this chapter. My advice? Pause right here, take a screenshot. These are your best friends when you're solving problems on work, power, and energy. Okay, time for a quick mental workout. Assertion, work done by kinetic friction is always negative. Reason, frictional force always opposes relative motion. So what do you think? Are they both true? And does the reason explain the assertion? Quick, think about it. And one more for you? Assertion, the work done by a conservative force around a closed path is 0. Reason, the work done is path independent. This goes right back to the core definition we talked about. You got this, right? Whew, we have covered a lot of ground, but it's so important to remember that in physics, nothing just stands alone. Everything connects. So let's talk about how what we just learned is going to pop up again in future chapters. So why does this all matter so much? Because mastering the work-energy theorem is your foundation for understanding the next huge topic in mechanics, collisions and systems of particles. That whole chapter is built on conservation laws, and you've just spent this session mastering one of the most important ones. By nailing this chapter, you're already setting yourself up for success in the next one. I'll leave you with this final thought. Physics tells us that energy is always conserved. But what about your energy? As a student, your time and your mental energy are your most precious resources. So are you conserving them for what truly matters? Revise smart, revise often, and you are gonna do great. Thanks for watching.